Good day, viewers and listeners. I welcome you all to another episode of our weekly online chemistry class. And this is episode 2 of the season 4. In the first episode, I introduced to you isomerism in organic chemistry. After defining what isomerism is, I also told you that we have two major types of isomerism, which are constitutional isomerism and stereoisomerism. We were able to conclude constitutional isomerism in the previous season. So today we are going to focus on stereoisomerism. But before we start, I want to implore you to try as much as possible to click on the subscribe button whenever you are watching any of our videos. And I wish you all the best. Thanks for watching. So stereoisomerism is a form of isomerism whereby two or more organic molecules differ only in the spatial arrangement of atoms or group of atoms in space. And we have two major types of stereoisomerism. The first is conformational stereoisomerism, while the other type is configurational isomerism. So let's start by looking at the conformational isomerism. What do we mean by conformational isomerism? Conformational isomerism is a phenomenon whereby two or more organic molecules interconvert when there is a rotation about carbon-carbon single bond, especially sp3 and sp3 hybridized carbon atoms, as in the case of alkanes, to be precise. So the various forms of the compounds obtained as a result of interconversion due to carbon-carbon single bond rotation are what we refer to as conformational isomers or simply conformers. So the study of the kinetic and thermodynamic properties of these interconvertible compounds are what we refer to as conformational analysis. Now, I want us to look at methane. If you look at methane, you will observe that methane only has one three-dimensional arrangement. Why? Because it contains only one carbon atom. There is no sp3 hybridized carbon atom resulting to a carbon-carbon sigma bond. But this is not the case in ethane. The ethane molecule, which can be written in this format, has carbon-carbon sigma bond. And as a result of that, there is possibility of rotation. We can twist this carbon about certain degree over the other one. And that is what brings about what we call conformational analysis. And this ethane can be represented either by using Newman perspective formula or using the Ash formula. So the Newman perspective formula will have something of this nature. If this is the first carbon atom, then this is the second carbon at the middle here. We can represent ethane in this format. This is a carbon 1, assuming each carbon having three hydrogen atoms. So this carbon represented by a cycle has 3 hydrogen atoms attached to it. The second carbon is this angle here, also having 3 hydrogen attached to it. This is Newman perspective formula. The other formula is what we have in this format: carbon, carbon. Then here you have the ash wedge, then the solid wedge, and you have the third hydrogen. Likewise, here you have something like this. Then you have the ash wedge, and you have the solid, something of this nature. So these two are representation of ethane. If we rotate the carbon-carbon single bond at about 60 degrees of each other, you have something of this nature, 60 degrees. When we rotate it, we are going to have another form of the ethane, which is of this format. So we have something like this: hydrogen, 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 hydrogen. Likewise here, we have something of this nature, carbon, carbon, then you have hydrogen, you have the ash, then you have the solid. Likewise here, you have something of this nature, hydrogen, hydrogen, and hydrogen. Now, looking at this, you will see that in this conformer, the arrangement, there is more space between the hydrogen atoms in each of the carbon atom in the molecule. Now, this type of conformer is what we refer to as staggered conformer. While here, the hydrogen are very close to one another, no much more space, and this is what we call eclipse conformer. So this is also eclipse conformer. This is staggered conformer. I want you to look at it in this angle. Look at this hydrogen. Look at this bond, similar to what we have in cis-trans isomerism. Look at this. They are far away from each other. Now, in staggered conformation, there is much more space. So that means the force of repulsion between the neighboring carbon-hydrogen bonds is much more minimal compared to what we have in eclipse. So as a result of that, the energy of the eclipse is higher than that of the staggered because of the repulsive forces, and we expect staggered to be more stable than eclipse. So the extra energy of the eclipse, which makes it to be less stable compared to the staggered, is what we refer to as torsional strain. Torsional strain. So that means torsional strain is found in eclipse conformer, but it is absent in staggered conformer. Meanwhile, both eclipse and staggered conformer can have what we call steric strain based on other group of atoms that are attached to each carbon atom where the carbon-carbon rotation is being taken place. I want us to look at in a situation whereby we have butane. Butane is CH3, CH2, CH2, CH3. This is carbon 1, this is carbon 2, carbon 3, carbon 4. So that means we can have rotation between carbon 1 and 2. And we can also have twisting of carbon 2 and carbon 3. Now, in the case of carbon 1 and carbon 2, I'm still going to be using the perspective formula, the Neumann perspective, for better explanation. Okay, we can have something of this nature. This is carbon 1, this is carbon 2, C1, C2 rotation of butane. So this is CH3, and this is CH3. So you have a carbon, a methyl group here, carbon, 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 making 4. And likewise here, we can have something like this. This can be CH3, while this can be CH3. So this is eclipse. Okay, okay. It is C1, C2. It is C1, C2. So this is going to be hydrogen. Sorry about that. Why this is CH2, CH3? Because if it is C1, C2, on C1 there are 3 hydrogen atoms, and this is the carbon. Okay, this is the carbon, the one in the cycle, 1, 2, 3. And on the carbon 2 there are 2 hydrogen and 1 ethyl group. So if this is the carbon, hydrogen, hydrogen, ethyl group. Likewise here, the eclipse form will be of this format, CH2, CH3. And these are the 2 conformers that are possible when you rotate carbon 1 against carbon 2 in butane to about 60 degrees. But in C2, C3, we can have up to about 6 conformers. Like for instance, you have something like this. We have about 6 conformers: hydrogen, CH3, hydrogen, 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 CH3. So when we rotate this about C2, C3 at about 60 degrees, we can have another conformer where we have something of this nature. Okay, that is hydrogen. Okay, CH3 here, CH3, hydrogen, hydrogen, hydrogen. Okay, now if you look at this, you will observe that the methyl groups are far apart from each other. Likewise, each of the other atoms attached to the carbon atom, but here they are close. So this is the staggered, while this is the eclipse. Now you can have another form of staggered, whereby this methyl group can be here, while this hydrogen here can come here. When this methyl group is here, it is also staggered, but that staggered cannot be compared to this staggered, where they are far apart from each other. So this one is anti-staggered, while the other one, when a methyl group is here, is called the gauche. G-A-U-C-H-E. Similarly here, you can compare this eclipse to an eclipse whereby this methyl group is here and this hydrogen is here. You can see they are much closer to each other, and that will give a greater repulsion. So this eclipse is much more stable than the other eclipse when the methyl group is closer to each other. So you have it in arrangement like that up to about 6. So this is what we call conformational analysis. This type of analysis is only found in saturated compounds, to be precise, alkanes, because there is no restriction. There can be rotation in the molecule about carbon-carbon single bond. And we also have it in cyclic organic molecules, cyclic alkanes. I want us to look at that. So if you have aliphatic alkanes with more than 4 carbon atoms, of course, you can carry out conformational analysis based on which carbon atom are you rotating against the other, whether carbon 2 against 3, 1 and 2, or 1 and 3, 2 and 3, 3 and 4, and so on and so forth, depending on the length of the chain. Now, in cyclic alkanes, the first 4 members are cyclopropane, we have cyclobutane, we have cyclopentane, and we have cyclohexane. So as the size of the ring increases, their stability also increases. So that means the larger the size of the ring, the more stable the cyclic alkanes. And what is responsible to that? For that, we call that angle strain or strain effect. We are coming to that. So in that case, so that means among these 4, cyclohexane is the most stable, while cyclopropane is the least stable, having the highest energy. Although this is not as stable as cyclohexane, which contains about 7 carbon atoms in the ring. Now, the strain effect occurs when there is a decrease in the bond angle as compared in the ring as a result of the ring formation, as compared to the conventional 109.5 degree bond angle that is commonly found in sp3 aridized carbon atoms. So here all the carbon atoms are sp3 aridized, but the bond angle here has been restricted to a certain amount. This is 60 degree compared to the conventional 109.5 degree. This is a right angle triangle, while this is around 120, and so on and so forth. So the stability of the molecule, this is 90 degree, is determined by the size of the ring. But most naturally organic compounds usually exist in cyclic form containing about 6-member rings, cyclohexane. And what is responsible for that? Cyclohexane is capable of existing in a conformer that is completely free of strain, and that is the chair conformer. So that means we have 2 types of conformers of cyclohexane. We have the chair, which is of this format. This is the chair conformer. Can't you see that it looks like a chair? That's a chair conformer of cyclohexane. 1, 2, 3, 4, 5, 6. So here you have the axial, you have the equatorial hydrogen. This is axial. The hydrogen that is protruding downward is the axial hydrogen. That is the axial bond. While the one that is protruding outside is what we refer to as equatorial bond or hydrogen. So this is this, okay? Likewise here, you have something like this, and you have something like this. Likewise, there is a possibility of rotation about the carbon-carbon bond in the cyclic ring. But unlike the aliphatic, when such happens, the only difference between the 2 conformers is just a change in equatorial bond changing to axial bond. So this is what we call ring flip. So when there is a ring flip, the axial bond here will change to the equatorial bond here. So this one will come here, while this one will now become the equatorial. Likewise, the arrangement will go over everything. That is the two conformers, both chair conformers that we have for cyclohexane. Now, the both conformer is like this. You have something of this nature in form of boats. Look at this. Of course, that looks like a boat. Good. That's a boat conformer. Likewise, you have the axial, the equatorial, the axial, the equatorial. You see this? You see that? That is the boat. And if you look at this, of course you expect one to be more stable than the other. This can also undergo ring flip, when there is a change of equatorial changing to axial and axial changing to ring. Although there is no angular strain in both conformer, the chair and the boat has no angular strain. But the the boat form has torsional strain, while torsional strain is completely absent here. Why? As a result of what we call the flag pole hydrogen. These two hydrogen here, they are flag pole hydrogen. And as a result of their orientation, it results in what we call torsional. Even if you look at this, you see that the hydrogen are much more closer in boat than in chair. And let me give you a natural phenomenon. Somebody, if you are traveling and you are seated in a boat, you sit less comfortable compared to when you are sitting on a chair. On a chair, you feel more balanced and more relaxed. And as a result of that, you can use that to explain the stability of the two isomers. So the chair conformer is much more stable than the boat conformer. What makes the boat conformer to be less stable than the chair is as a result of what we call torsional strain. Although both can have what we call steric strain, depending on the group of atoms that is attached to either the equatorial or the axial bonds in each atom. So this is what we call conformational analysis. You are expected to be able to define that. You are expected to know the meaning of conformer or the rotamers. They are expected to know what we call the conformational isomerism. And likewise, you must be able to distinguish between the staggered and the eclipse in terms of energy and stability. You are also expected to be able to distinguish between the chair and the both conformers of cyclohexane, among others. And don't forget, you can use that to also explain the differences in the substituted cyclohexane. Like for instance, if you have 1,2-dimethylcyclohexane, of course they can also exist in chair and both conformer. Thank you for listening. In our next edition, we are going to discuss geometric isomerism. Stay blessed.